Hello, and welcome to this presentation on standard graphs. We're going to look at some common curves that hopefully you're familiar with, and we're going to recap some of their properties that will help underpin further work. Presentation overview of standard curves. We're going to recap straight lines having the form y is equal to mx plus c. Quadratic curves have the form y is equal to ax squared plus bx plus c. And cubic curves of the form y is equal to ax cubed plus bx squared plus cx plus d. We'll also look at trigonometric functions, y is equal to sine x, y is equal to cos x, and y is equal to tan x, etc. The equation of the circle, x minus a all squared plus y minus b all squared is equal to the radius squared. The ellipse of the form x squared divided by a squared plus y squared divided by b squared is equal to 1. The hyperbola of the form x squared divided by a squared take away y squared divided by b squared equals to 1. The rectangular hyperbola, y is equal to c a constant divided by x. And we'll look at logarithmic curves, y is equal to log to the base b of ax, and specifically look at the natural logarithm y is equal to ln x. Then we'll review the inverse function to the natural log curve, which is the exponential curves of the form e to the ax. And finally we'll review polar graphs, y is equal to r theta. Here's a slide of some common graphs we'll be considering. The linear graph, y equals mx plus c. The quadratic curve, parabolic shape of y equals ax squared plus bx plus c. Cubic graph, y equals ax cubed plus bx squared plus cx plus d. And we'll be looking at the circle, the ellipse, the parabola associated with the quadratic graph. We'll be looking at trig functions, sine, cos, tan, etc. We'll be looking at the hyperbola section, looking at logarithmic functions shown here, exponential functions shown here, and also polar graphs, the r theta graphs as shown plotted here. Standard curves. When the mathematical equation is known, coordinates can be calculated over a limited range of values and the equation depicted graphically within the range of the calculated values. It's often useful to show the characteristic features of the equation, and this can be done with a sketch of the equation without necessarily accurately plotting the points. This approach is termed curve sketching and can involve the use of differential calculus, for example, if we want to calculate the actual location of a turning point. If y depends on x, then in mathematical speak, y is said to be a function of x, and the relationship is expressed as y is equal to f of x. In this case, x is termed the independent value and y is termed the dependent value. Within engineering and science, corresponding values are often obtained from results of experimental tests. The following slide provides a summary of common curves found in practice. We need to be aware of these curves and their characteristics, as this knowledge underpins further work. Let's consider straight lines. The general equation of a straight line is y is equal to mx plus c, where m is the gradient or the slope, often denoted by delta y by delta x, and c is the intercept with the y-axis. Note it's with the y-axis, not the x-axis. What we're going to do here is sketch the following four lines, labelled A, B, C and D, on our graph. Each of the lines of the form y equals mx plus c. I would encourage you to stop the presentation to see if you can sketch these lines before looking at the solutions over the page. There's some hints here. Taking equation A, we've got y is equal to mx, so the m is 2.5 plus c, so the c is plus 1.5. So we know for this line it will pass through 1.5 on the y-axis because that's the value of c in this case. The gradient is 2.5, so that's 2.5 in 1. So basically if we move 1 in the horizontal direction, we will move 2.5 in the vertical direction. Now, because the increments of the axes in this particular diagram are the same, each of the increments is 0.5, I can literally count squares here. So if I move 1 in the horizontal, I will move 2.5 squares in the vertical. So that will then give me a second point here for my graph. So my line, if I was to sketch a line through those 2 points, would be something like that. That would be the line y is equal to 2.5x plus 1.5. What I've done there is move 0.5 in the horizontal and 1.25 in the vertical. And of course that's the same as going 1 in the horizontal and 2.5 in the vertical to give the gradient of 2.5. Considering line B now, we've got y is equal to 2x minus 3. So in this particular case, we know the line will cross through minus 3 on the vertical axis, and the gradient is positive 2. So again, if I count squares here, I will go 1 in the horizontal and 2 in the vertical, and that will give me another point on the line I can plot. So drawing a line through those 2 points will give me the line of B. Notice the gradient of the red line is steeper than the gradient of the blue line, which of course is expected because the red line has a gradient of 2.5 and the blue line a gradient of 2. Now if we take line C, we need to be a bit careful here. We've got y is equal to minus a half x minus 1. So that minus x upon 2 is really minus a half x. So the negative means we've got a negative gradient there, and it crosses the y-axis at minus 1. So we know the line is going to cross at this point here on the y-axis, the minus 1. Now this is the gradient of half. So basically if we move 2 in the horizontal, I'm going from right to left here because of the negative gradient, we only move 1 in the vertical, and that gives us the gradient of a half. If we draw a line through those 2 points, we will get the gradient of line C. Again, negative gradient, so it's going in a different sense to the blue and the red lines, which are positive gradients. It's also a shallow gradient because it's 0.5, so it's obviously shallower than the blue and the red lines. If we take the last line, the y equals x, now you've got to see that as y is equal to 1x plus 0. So that's the y is equal to mx plus c equation. The 1 we don't write, but the 1 is there, so the m is 1, and there is no c value, so the c must be 0. So this is a 45-degree line that will pass through the origin, 0, 0, and if we move 1 in the x, we move 1 in the y. So in this case, if we move 0.5 in the x, we would move 0.5 in the y to give us a second point. So our line drawn here for the y is equal to x is simply a 45-degree line. The full solutions are shown on the next slide. So here are the solutions to the straight lines. I'll let you review this slide yourselves. I've used colour here to try and distinguish quite clearly the different lines involved. Quadratic equations. The general form is y is equal to ax squared plus bx plus c. A relates to the steepness of the curve, and if it's a positive a, it means it's a bucket shape. So a positive a would be this kind of shape, and a negative value of a is a hat shape, which would be this kind of shape here. And as I said, the a relates to the steepness of it, so the larger the magnitude of a, the steeper the sides of the curve. Another characteristic of the quadratic curve we need to be aware of when trying to sketch them is the ratio b divided by a. This relates to which side of the y-axis the vertex is located. And the vertex is the top of the quadratic curve in this case, and the bottom of the quadratic curve in this case, where the gradient of a tangent to that point is 0. If the b upon a ratio is positive, then the vertex is on the left hand side of the y-axis. If the b upon a ratio is a negative, then the vertex is on the right hand side of the y-axis. The c in the general equation y equals ax squared plus bx plus c is again the intercept with the y-axis as it is with a linear equation y equals mx plus c. The c relates to the intercept constant. If we actually want to work out the location of the vertex in the x direction, the formula shown here without proof is minus b divided by 2a. That gives the exact location in the x direction of how to find the vertex. If we want to find the y location, in other words the coordinate of the vertex, we put the value of x into the general equation shown above. You can also find the vertex by using differentiation. Exercise 1Q relates to the sketching of quadratic curves. What we're going to be given here are equations, and we're asked to choose the appropriate sketch out of the solutions given to us that relates to the equation. To do this, you need to consider the constants a and c specified in each of the questions, and also consider the b upon a ratio, as that relates to which side of the y-axis the vertex lies. And knowing those characteristics, we should be able to ascertain which is the appropriate sketch to choose. So there are 6 questions we are asked to review here. I'm going to let you ponder each of them and decide which of the solutions relates to each of the equations given. So question 1Q and 2Q are shown below. Question 1Q, we're given y is equal to x squared. You've got to decide which of the 4 sketches shown below, A, B, C or D, equates to the sketch for y is equal to x squared. Question 2Q, you're given y is equal to x squared plus 2. You've got to choose your solutions, A to E here. Quadratic curve sketching continued. Question 3Q, you're given the equation y is equal to minus 2x squared. You've got to decide which of the solutions A to E is the correct sketch. Question 4Q, you're given y is equal to 4 minus x squared. Again, you've got to choose which of the solutions is the correct sketch. Question 5Q, the quadratic equation given is y is equal to x squared minus 3x plus 2. We'll decide which is the solution, A to E. And finally, question 6Q, you're given y is equal to x squared plus 4x plus 4. And again, you've got to choose the solution A to E. The following slides show you the solutions. So for question 1Q, we're given y is equal to x squared. Now don't forget, the quadratic has a general form of y is equal to ax squared plus bx plus c. So in this particular case, the actual value of the a is 1. Don't write the ones, but it's there, and there is no b or c term in this case. So we're looking at a quadratic curve that's symmetrical about the y-axis and goes through the origin 0, 0. So I think it's clear to see solution in this case would be b. The a curve cannot be correct because it doesn't go through the origin 0, 0. C cannot be correct because it goes through a value on the y-axis below 0, and D cannot be correct. Although it does go through the origin 0, 0, it's an inverted curve, so that would only be true if the a was negative 1. Looking at question 2Q, we're given the equation y is equal to x squared plus 2, and again notice that's 1x squared. So in this case we've got no b value, so there'll be no shift in the vertex left or right, so it'll be a symmetrical curve. Because the c value is 2, that means it's shifted above the origin by 2 increments. So looking at our curves here, the solution in this case must be D. It cannot be A because that's an inverted quadratic, so that's not correct. It cannot be B because that shows the vertex is shifted to the right and there's no shift in vertex. It cannot be C because again a shift in vertex. And it cannot be E because that goes to the origin 0, 0, but the C in this case is positive 2. So it has to be D. Question 3Q solution. We're given the equation y is equal to minus 2x squared. In this case the A is the minus 2, so that means we're going to get a hat shape. There is no B or C term in this equation. If there's no B term, there's no shift in the vertex, and there's no C term, it means the vertex will go through 0, 0, the origin of the graph. So we're looking for a curve that's a hat shape, symmetrical about the y-axis, and the vertex passes through the origin 0, 0. The only curve that shows us those features is E. It cannot be A because the vertex doesn't pass through 0, 0. It cannot be B because that's not a hat shape. It cannot be C, that's not a hat shape. It cannot be D because the vertex doesn't pass through 0, 0. So it can only be E. Question 4Q solution, we're given a graph of y is equal to 4 minus x squared. Now be careful here, the 4 is actually the constant c, and the minus x squared is actually the ax squared term. Again, notice that there's a 1 in front of the x, so it's minus 1x squared in this case. So again, if we've got a negative a term, that means we're going to have a hat shape. The 4 for the c means we're going to cross it 4 on the y-axis. There is no b, so there is no shift in the vertex. So looking at the curves, the only solution we can have is A. A shows the vertex passing through 4. It's of a hat shape and it's symmetrical about the y-axis. It cannot be B because B shows the vertex being shifted. It cannot be C, again the vertex has been shifted. It cannot be D, the vertex is shifted. And it cannot be E because it's not a hat shape. Solution to question 5Q, we're given the equation y is equal to x squared minus 3x plus 2. So in this case the A value is positive 1, the B value is minus 3, and the C value is positive 2. So we will get here a shift in the vertex. If you look at the B upon A ratio, that will be a negative ratio. So the vertex will be on the right hand side. It's also got to pass through the y-axis at positive 2. So looking at the diagrams here, the one that seems closest to that shape would be C. The C curves show the vertex on the right hand side of the y-axis, so that follows the negative B upon A ratio. It shows a C value on the positive on the y-axis, and it's a positive A value because it's a bucket shape. It cannot be A because the vertex on the left hand side is not true. It cannot be B because again the vertex on the left hand side in this particular case. It's unlikely to be D because though the vertex on the right hand side, the y value would cross at a higher value than 2, we would estimate there, although that is slightly subjective. And the same for the E curve, the vertex is on the right hand side, which is correct, but again the way the curve would actually cut the y-axis would seem to make the y value rather greater than 2. So I suggest that curve C relates best to the equation given. And finally question 6Q, we're given the equation y is equal to x squared plus 4x plus 4. So we've got an A value of 1, a B value of 4, and a C value of 4. So in this case we've got a positive B upon A ratio. The vertex will be on the left hand side. The only solution that has a vertex on the left hand side is B. So B looks like the solution to this equation. Cannot be A because that's showing a symmetrical curve at the y-axis, so that would assume B value is 0 and our B value is 4 in this case. It cannot be C because that shows the vertex on the right hand side, which is not true in this case, and it cannot be D and it cannot be E for the same reasons. So the solution here would be B. Cubic equations. They have the general form y is equal to ax cubed plus bx squared plus cx plus d, where d in this case is the intercept with the y-axis. What's shown below on the graph is the equation y is equal to x cubed. What we're asked to do is sketch the equation y is equal to x cubed plus 10. I'll let you think about that for a moment. How would you sketch the curve y is equal to x cubed plus 10 on that graph? The solution is shown on the following slide. So plot of the cubic equations. So we were given y is equal to x cubed on the previous slide. What I've done here is add the curve y is equal to x cubed plus 10. Basically it's a shift in the vertical axis because the d value in this case was plus 10. Trigonometric equations. Again, we've seen these before. Y is equal to sine of an angle, sine theta in this case, y is cos of theta, y is tan of theta, and we usually plot these between 0 and 360 degrees or 0 and 2 pi radians. I would encourage you to sketch the sine and cosine curve on the diagram below. So what does the sine curve look like between 0 and 360 degrees, and what does the cosine curve look like between 0 and 360 degrees? Curves shown on the next slide. Here's a plot of the sine and cosine waveforms. The sine waveform is shown in the bold line here. This is a sine waveform. It goes up to maximum amplitude of 1 between 0 and 180 degrees, and then down to -1 between 180 degrees and 360 degrees. It's classified as a continuous periodic curve. It goes on forever, repeating itself every 360 degrees. The cosine waveform is shown here in a lighter curve. It starts at 1 amplitude and it goes down to -1 at 180, and then it returns up to 1 at 360 degrees. So it's a 90 degrees phase shift from the sine curve. Again, it's a continuous periodic curve. It goes on forever, repeating itself every 360 degrees. Here's a plot of the cosecant curve, the 1 upon sine curve, the reciprocal of the sine curve. It starts at positive infinity to begin with, it's the value of 0, and has this shape between 0 and 180 degrees, and then here comes perhaps a negative infinity, and has this shape here between 180 degrees and 360 degrees. And also as a plot of the secant waveform, that's the 1 upon cos function, or reciprocal to cos function, and that shows a curve here between 0 and 90. It goes off to positive infinity at 90 degrees, comes back from negative infinity at 90 degrees through to 1 here at 180, and then goes off again to negative infinity at 270, and then back from positive infinity at 270 to 360. So just for reference there, that's the cosecant and the secant curve, the reciprocal of the sine and cosine curve respectively. I'd encourage you to sketch the tangent curve here between 0 and 360, so one cycle again of the tangent curve showing the discontinuities associated with it. Solution is shown on the next slide. Here's a plot of the tangent curve. It starts at 0 and goes towards positive infinity as it approaches 90 degrees. It comes back from negative infinity just after 90 degrees through to 0 at 180 degrees, and then off to positive infinity again as it heads towards 270 degrees, and then back from negative infinity at 270 degrees through to 0, and again repeats itself. The tangent curve is classified as a periodic curve. It repeats itself every 360 degrees, but it's classified as a discontinuous curve as it jumps to positive and negative infinities throughout its cycle. Here's a plot of the cotangent curve, the reciprocal of the tangent curve. It shows it starting at positive infinity, going through to 0 at 90 degrees, then off to negative infinity as it heads towards 180 degrees, and then comes back from positive infinity just after 180 degrees through to 0 at 270, off to negative infinity as it heads towards 360 degrees. Again, it's a periodic waveform, but it's a discontinuous waveform. Let's look at the equation for a circle. The simplest equation is x squared plus y squared equals to r squared, where r is the radius of the circle. And in this case, this circle would have its centre at the origin. The general equation is x minus a all squared plus y minus b all squared is equal to r squared. This is again a circle of radius r, but its centre is at location a comma b. The diagram on the right hand side shows you an equation in the simplest form, the x squared plus y squared in this case equals to 4, where the radius is 2. The circle continues. We're given an exercise here. We're told that a is equal to 2, b is equal to 3, and r is equal to 2. We're asked to determine the coordinates and then plot the circle. So from the general equation x minus a all squared plus y minus b all squared is equal to r squared, first of all we need to rearrange the equation to make y the subject, and then put in the values given above into the equation, we can find the values of y. So I'm going to ask you to rearrange the above equation to make y the subject. So basically you're going to take the x minus a all squared from both sides, then you're going to square root both sides, and you're going to add b to both sides, but I'll let you go through that process. And then you're going to work out the coordinates of y given an x is equal to 0, you can find the value of y. When x is equal to 1, there will be two values of y because of the plus or minus you get when you take a square root of both sides of the equation. You'll see that when you transpose it. Put the x value of 2 in, and again there'll be two values for y. The x value of 3, there'll be two values for y. And when you put the x value of 4 in, you'll just get one value of y. I would encourage you to go through the process of rearranging the equation and finding the coordinates of y, and then sketching the circle. Solution is shown on the following slide. The circle continued. Reviewing the exercise here, we were given that a is equal to 2, b is equal to 3, and r is equal to 2. We're asked to determine the coordinates using the generic equation for the circle and then plot the circle. So from the generic equation for a circle of x minus a all squared plus y minus b all squared is equal to r squared, we have to rearrange for y. So to do that, what we do is take x minus a all squared from both sides to give us y minus b all squared is equal to r squared, take away the x minus a all squared. Then we square root both sides, so we get y minus b is equal to the square root of r squared minus x minus a all squared on the right hand side. And then we simply add b to both sides, and that leaves us with y is equal to the square root of, in square brackets here, r squared minus the x minus a all squared, with the bracket, plus the b. Note that the b is outside of the square root sign here. We're given in the question that the r value is 2 in this case, the a is 2, and the b is 3. Now we can work out our coordinates. We're given the values of x from 0 to 4. All we do is put these values into the equation for y and find the values of y. So in this case, when x is 0, y is equal to 3. There's only one value in this particular case. But when you put the value of 1 in the equation, you will find there are two values of y in this particular case because of the square root of the square bracket above. The same occurs when you put the value of x of 2 into the equation. There are two values of y, and the same for 3. There are two values of y. When you put the x value of 4 into the equation, you will get one value of y in this particular case. Here are some example calculations relating to the exercise for the circle. So when x is equal to 0, we work out the value of y. When x is equal to 1, we work out the value of y, and there are two of them because of the plus or minus. So two values of y when x is equal to 1, and the same when x is equal to 2 and x is equal to 3. I'll let you wander through the solutions if you want to see the detailed calculations. The circle continued. Here's a plot of the equation x minus 2 all squared plus y minus 3 all squared is equal to 4 for your reference. Notice the origin of the circle is a equal to and b is equal to 3. Radius is 2 in this case. The ellipse. The general equation for an ellipse is given as x squared upon a squared plus y squared upon b squared is equal to 1. The general shape is shown in the figure on the right hand side here. We'll give an exercise to review. We're told that constant a is equal to 3 in this case and constant b is equal to 2. We're asked to calculate the following points for the ellipse. So we're given the equation x divided by a all squared plus y divided by b all squared is equal to 1. We first of all need to rearrange the equation to make y the subject. Once we've found the equation for y, we simply put the values of x, given here, into the equation to work out the values of y. What you'll find is there will be two values of y, a plus or minus in most cases. I would encourage you to stop the presentation, rearrange the equation for y, put the values of x in, and find the coordinates for y. Solution is shown on the following slide. The ellipse continued. The exercise given gave us constants a of 3 and b of 2. So rearranging the equation for the ellipse, the general equation given here, we should find that y is equal to the square root of 1 take away x divided by a all squared multiplied by b. Notice the b is outside of the square root. Putting the values in here, the value of a we're given in the question is 3 and the value of b is 2. Don't forget, when you take a square root there's always two solutions, so that's why when we put our values of x in, you'll find in most cases there will be two values for the y, a plus and a minus. I'll let you work out the y values there. Detailed calculations are shown over the page for reference. This is the ellipse continued. Here's some example calculations. When x is equal to 0, we can work out two values of y, again because we've got a plus or minus because of the square root. There are two values of y. X is equal to minus 1, again there will be two values of y, and so on. I'll let you go through the calculations at your leisure. A sketch of this particular ellipse is shown here. This is the x squared upon 9 plus y squared upon 4 is equal to 1 equation. Notice that the a is equal to 3 and the b is equal to 2 in this case. The hyperbola. The general equation for the hyperbola is x squared upon a squared take away y squared upon b squared is equal to 1. Given an exercise here, we're told that constant a, in this case, is 3 and b is 2. We're asked to calculate the points on the hyperbola given the table below. So what we need to do first of all is take the general equation for the hyperbola and rearrange it so that y is the subject of the equation. Once we've done that, we put the values of x, we're given a range of -6 through to +6, and we calculate the values of y, and there will be two values of y in most cases. So I'll let you rearrange the general equation for hyperbola to make y the subject and put the values of x in to calculate the values of y. Solutions are shown on the following slides. General hyperbola continued. So we were given in this particular question that the a was equal to 3 and the b was equal to 2. First thing we needed to do was to rearrange the equation to make y the subject. So rearrangement is shown here. So the first step is to take the x all squared term from both sides of the equation. To leave, you would be careful here, the negative y divided by b all squared. What I do then is multiply throughout by -1 to change the sign of all the terms. So I get a positive y divided by b squared on the left hand side is equal to -1 plus the x divided by a squared on the right hand side. So on the next line, what I've done is square root both sides to get rid of the squared on the left hand side and then multiply both sides by constant b. So I end up with y is equal to the square root of, in square brackets there, the x divided by a all squared, take away 1, and that is multiplied by b. Again, b is outside of the square root sign. Putting the values in, we know a is equal to 3 and b is equal to 2 in this case. So given values of x ranging from -6 to +6 in this particular case, we can work out the values of y. And notice there are two values of y in most cases. Detailed calculations are shown over the page. The hyperbola is continued. Here are some example calculations. When x is equal to -6, we can work out the value of y. Again, because of the square root, it's a plus and minus term, so we end up with two values of y, or a value of x of -6, and the same when x is equal to 4, we'll end up with two values of y. But I'll let you look at those calculations at your leisure. On the graph is shown a hyperbola to the right hand side of the y-axis, with the coordinates of positive x, and a hyperbola on the left hand side of the y-axis with the coordinates of the negative x. This is the hyperbola for the x squared upon 9 minus y squared upon 4 equals to 1 equation. Notice where the a is equal to 3 and the b is equal to 2 values occur. The rectangular hyperbola has the general equation y is equal to c divided by x, or you could write that as y is equal to c times x to the -1. Or it could be rearranged that x times y is equal to c. So in the exercise given here, we're told that c is equal to 9 in this particular case, and we're asked to calculate the following points and plot the rectangular hyperbola. In this case, the equation is already given in terms of y is equal to c divided by x. So given values of x, from -8 to +8 in this case, we can calculate the values of y, and I'll let you do that. Once you have the coordinates, you can then plot the rectangular hyperbola on the graph. Solution shown on the following slides. Rectangular hyperbola continued. We're given the general equation y is equal to c divided by x. In this particular exercise, we're told that c is equal to 9. So from the general equation, y is equal to c divided by x. In this case, y is equal to 9 divided by x. So we can work out the values of y given the various values of x from -8 to +8. These are our values of y, etc. I'll let you go through the process of doing the calculations. The plot of the rectangular hyperbola is shown on the following slide. Here's a plot of our rectangular hyperbola on the positive side of the x-axis and on the negative side of the x-axis. Notice that c is equal to 3 defines this point here. Let's look at logarithmic functions and logarithmic curves. From a previous presentation, we looked at a definition of a logarithm, which states that x is equal to log to the base b of y can be written in the form of y is equal to b to the x. And we can go from left to right or right to left with the definition. The x equals to log to the base b of y is logarithmic form, and the y is equal to b to the x is the exponential form. We're going to use the logarithmic form to look at logarithmic functions, and we're going to find that when we draw them, they'll all have similar shapes. This is shown in the exercise on the following slide. In this exercise, we're asked to plot the common logarithm, that's log to the base of 10, and the natural logarithm, that's log to the base of e, the exponential, over the range of 0.126, as shown in the table. Notice that in this case, the x-axis is actually labelled y, so on the x-axis, traditional x-axis, we would call that number y, and the y-axis is actually labelled as logarithm x. So the two functions we're going to work out are x equals to log of y, that's log to the base 10 of y, the common logarithms, and x equal to ln y, that's log to the base e of y, the natural logarithms. So I suggest you work out the values from your calculator and fill in the table appropriately for the two log functions, and then sketch the log curves on the graph below. The solutions are shown on the next slide. So here are plots of the logarithmic curves. We were initially asked to find points on the log to the base 10 curve and x equals to ln y, the log to the base e curve. These are the values you should have calculated. I suggest you check your values with the table stated here. In the graph below, we've plotted these two functions, the x equals to log to the base 10 of y and the x equals to ln y are plotted on the curve. But I've also plotted other functions. We've got log to the base 2 of y, log to the base 3 of y, 4 of y, and so on, up to log to the base 9 of y. And what you notice with all these curves is they all have a very similar shape. Looking at their characteristics, notice that they all pass through the y value on the horizontal axis of 1. This can be shown from the exponential form of the definition, the y is equal to b to the x. The only way we can get a value of 1 on the left-hand side for y is to have an index value x of 0. So in other words, when y is equal to 1, the logarithm x must be equal to 0. We can also see a characteristic that when the logarithm on the vertical axis is 1, so when x is equal to 1, if we draw a horizontal line across, it always hits the curve and gives a value equal to the base. So for example, if we take this curve here, which is ln2, if we draw the horizontal line across till it hits ln2, it hits it at a y value of 2. And this can be seen for all curves. It's not easy to see for the other curves, but for the ln10 curve here, you can see again, if we draw the horizontal line across, it hits the curve at a value of 10 on the horizontal axis. And again, this is shown from the y is equal to b to the x, because to get the value of b on the left-hand side of the equation over here, the only value of x we can ever have is 1, because anything to the power of 1 is itself. So to get the value of 10, say, on the left-hand side for y, then we must have 10 to the power of 1 on the right-hand side. And that applies to any base. And the final characteristic we note is that all the curves tend towards negative infinity. We're only showing them going to -3 here, but actually they tend to negative infinity. And again, that's because of definition. If we want to have 0 on the left-hand side for y, the only way we can achieve that is to have a negative index for the x, and it has to be a very, very large negative index to approach 0. So summarizing logarithmic functions, on the previous graph we had the log of base 2 through to the log of base 10 plotted, and we noticed that all the logarithmic functions had a very similar shape. Looking at the characteristics of the log curves, a logarithm of the number 1 equals to 0 for any base. The logarithm of the base itself always equals to unity, equals to 1, and the logarithm of 0 always equates to negative infinity. The curve tends to negative infinity as we approach a logarithm of 0. If you want more information about the characteristics of logarithms, I suggest you review the presentation specifically on the definition of a logarithm. Exponential functions considered here. The general shape of the function y is equal to e to the x is shown below. This is the curve here. It's been plotted for us. This is y is equal to e to the x. And what we're asked to do here is plot the function y is equal to e to the minus x between the range of -3 and +3 in increments of 1. So I'll let you work out the values for e to the minus x for this row here. Answers are shown on the following slide. So we were asked to calculate on the previous page the values for e to the minus x between -3 and +3. So here are the values stated. You can check your values against these in the table. And if we plot the e to the minus x curves, we get this shape, which is a mirror image of the e to the x curve about the y-axis. We're now going to consider polar functions and polar curves. The equation of a polar curve is written in the form r, the radius, is equal to some function of angle theta. On the right hand side is shown a polar diagram starting from 0 degrees here and moving in 30-degree increments in this particular case as we go anti-clockwise from 0. What is important to note about polar diagrams is that positive angles of theta are always measured anti-clockwise from this horizontal position, this 0 position. So this is positive angle theta, and it's very important that we remember that. We must always specify positive angles from this point in a anti-clockwise direction. If we want to measure the angle theta in a negative sense, we can do. Negative angles of theta are measured in a clockwise direction from the 0 position shown above. So in a table here on the left hand side we're given a radius and an angle. We're going to plot these various points. So given a radius of 2 and an angle of 60 degrees, then on our diagram we go to the radius of 2 line here, we go round to 60 degrees and we plot our point. This is the point radius of 2 and angle of 60 degrees. If we take our next point, which is given a radius of 3.5 and an angle of 140 degrees, the 3.5 radius is somewhere out here, and the angle of 140 degrees, if we follow round, this would be round about here. So this is the point radius 3.5 and angle 140 degrees. If we now look at the radius given as -3 and 30 degrees, we need to be slightly careful here. The best way to deal with the negative radius is to think of it in the positive sense initially and plot it and then reverse its direction. So if we had a positive value of 3 and an angle of 30, it would actually be this location here on the radius of 3 and angle 30. But because it's a negative 3, what we do is simply reverse the direction, so we plot it on this side of the diagram. So this is a radius of -3, an angle of 30 degrees. If we consider a point having a radius of 2.5, an angle 270 degrees, again 2.5 is somewhere between the 2 and the 3 mark, and we go around to 270 degrees, we'll plot the point here. This is radius 2.5 and angle 270 degrees. Now if we consider the coordinate 3 radius and -30 degrees, then negative angles of theta we said were measured in a clockwise direction from the horizontal, so the -30 degrees would give us a point here at the radius of 3. So this is radius 3, angle -30 degrees. If you wanted to put that in a positive angle, that would be radius 3 and angle 330 degrees would give the same position. So just to reiterate, if you have a negative radius given, what we do is consider that initially as a positive radius at some angle, we plot that point and then simply reverse its sense to get the negative radius direction. Polar functions continued, we're asked now to sketch the polar curve of r is equal to sine of angle theta. So in the left hand column of my table I have angle theta, and I've used degrees here from 0 degrees to 60 degrees, and on the right hand side I've got my radius, which is defined as r is equal to the sine of theta. Some of the values have been worked out for us. Sine of 0, and your calculator will be 0, make sure you're in degree mode. Sine of 30 degrees is 0.5, sine of 60 degrees is 0.866, sine of 90 degrees is 1. When you look at sine of 180 degrees, you get 0, but sine of 210 degrees you'll find is minus 0.5, and so on. I encourage you to check those values and also fill in the blanks in the table. Once you've completed the table, then I suggest you try and plot the points on the polar diagram on the right hand side. One thing to note when you're constructing a diagram is what happens to points that have angles greater than 180. Don't forget that the maximum amplitude of a sine waveform is 1, so the maximum radius you need to plan for on your diagram is 1, so I would suggest you've got increments of 0.25 for these rings in the diagram. If we plot just a few points just to get you going, the first point of 0, 0 would be here, then at 30 degree angle we've got a 0.5 radius, so that would be to our scale out here, and if you look at the 60 degree we've got a 0.866 radius, so that will be somewhere out here, and so the points will go on. Once you've plotted the points, put a nice curved line through them and see what shape you define. So I'll let you complete the table and plot the diagram. The full solution is shown on the following slide. Polar graphs continued. We were looking at the r is equal to sine theta function. Here's the full table of angle theta and the values of r. On the right hand side is the graph, or you should have found is a circle is plotted. If you plot all the points, you will get for the first 180 degrees the circle, and if you plot from 180 degrees through to 360 degrees, you actually retrace your steps because these are negative radii. We just take an illustration of that. If you take the point at 210 degrees, it's a value of minus 0.5 for the radius. So 0.5 at 210 on our scale would be here. But don't forget we reverse the point for a negative radius, so we end up plotting back at the 30 degree 0.5 position. The same applies to the other negative radii. So what we end up eventually is a circle on a polar diagram that represents the sine theta function. Polar functions continued. We're asked now to sketch a graph of the function r is equal to 3 theta between the range shown in the table below. Notice the angle theta will be in radians, and so the radius r range in this particular case will be from 0 to approximately 30 units. So in a moment we need to make our increment on our polar diagram from 0 to 30 on this horizontal axis. So given the function r is equal to 3 theta, the angle theta must be in radians in this calculation, although I have shown it in degrees in the table just for ease of reference, because we usually relate more so to degrees than we do to pi radians, but nevertheless in the calculations we must use the radians value. What I have done in a table is work out some of the r values already for value of theta radians of 0, we get an r value of 0 from the r is equal to 3 theta formula. When the theta value is actually pi upon 6, we actually get a value of half pi for the r value. I've written that as decimal, the two decimal places 1.57. When the theta value is pi upon 3 in radians, the r value is actually pi, but I've written that as 3.14 to two decimal places. When angle theta in radians is pi upon 2, and 3 times theta gives you 3 times pi upon 2, that's 1.5 pi as a radius, or a radius of 4.71 to two decimal places. I'll let you work out the other values of r given values of theta. I've just worked out the last value of r based on the theta value of 3 pi radians. So 3 pi radians times by 3, that's actually 9 pi, and that's actually a value of 28.27 in terms of decimal. So the arrangement of the radius has to be accommodated on our polar diagram is from 0 to approximately 30 units. Although the increments on the polar diagram shown are in terms of pi radians, don't forget you can think in terms of degrees as that helps you. So pi upon 6 is actually 30 degrees, pi upon 3 is 60 degrees, pi upon 2 is 9 degrees, etc. And also once you go past the 2 pi or the 360 degree plotting, don't forget you're starting around again. So 13 pi upon 6 is actually 30 degrees again. So 13 pi upon 6 will be plotted here, 7 pi upon 3 will be plotted here, and so on. So we go through a cycle of 1.5 revolutions, if you like. The 3 pi radians is 1.5 revolutions, or 540 degrees. I encourage you to complete the table, working out the values of r based on the theta values in radians, and then plot the points on the diagram. The full solution is shown on the next slide. Polar functions continued. Here's a solution for the r is equal to 3 theta problem we had on the previous slide. We were given values of theta in radians. I've actually shown them in this table in terms of degrees also, and also decimal radians for reference. And given the values of theta radians, we were able to work out the values of r corresponding to the r is equal to 3 theta formula. In other words, it's just 3 times the angle in radians. The table was split into two segments to cover the entire range of 0 to 3 pi radians. If you now plot the points from the table onto the polar diagram, you get what's called an Archimedean spiral. So you should see a shape like this when you plot your points, calculating the table for r on the polar diagram. And this is an r is equal to 3 theta diagram, an Archimedean spiral. Polar functions continued. Question 1p asks us to sketch between 0 and 360 degrees the following curves on polar graph paper. Part 1, r is equal to 2 times cos of angle theta. Part 2, r is equal to 3. So think that through to yourself. For any angle theta, the r is equal to 3. So what curve would you sketch there? For part 3, theta is equal to 120 degrees. And again, think that through. For any radius, the angle is 120 degrees. So what kind of diagram would you sketch there? Part 4 is r is equal to the angle theta. Part 5, r is equal to sine squared theta. Just be careful with that. That wants you to find the sine of the angle and then square the sine of the angle. Part 6, r is equal to cos squared theta, so again be careful, find the cos of the angle and then square that value. Part 7, r is equal to 3 times sine 2 theta. It might just help here to think of a bracketed term around the 2 theta, so multiply the angle theta by 2, then find the sine of it, then multiply it by 3, and that equals to r. And part 8, r is equal to sine of 3 times theta, so once again it may help thinking of a bracket around the 3 theta. So you're multiplying the angle by 3, then you're finding the sine of the angle, and that is equal to r. I would encourage you for each of the questions to lay your table out in terms of theta is equal to 0 degrees through to 360 degrees as shown here. If you want to write it in radians, that will be 0 through to 2 pi radians. I've used in 30 degree increments here, or pi upon 6 increments in radians. I suggest you fill in a table for each of the value of thetas, work out the value of r dependent on the function given, and then plot these shapes on a polar diagram. The answers to question 1p, parts 1 to 8, are shown on the following slides. Here is a slide of polar graph paper for your reference should you want to print this page and use this for your solutions. Polar graphs continued. Here are the solutions for questions 1p, all plotted on polar graph paper. Here is the bibliography used to create the presentation. Some very good technician engineering textbooks I would encourage you to refer to. I hope this has been of interest to you, and thank you for viewing.